Welcome back. Everything we have built so far, rectifiers, clippers, clampers, the Zener regulator, has one thing in common. They shape a signal or they limit it. None of them can make it bigger. But think of a microphone. It gives you a few millivolts, and a loudspeaker needs volts. Somewhere in between, the signal has to be amplified. For that, we need a completely new kind of component, one where a small current commands a much larger one. That component is the transistor. Today we meet it properly, its structure, its two families, and the simple current rules that, next time, will let us solve our very first transistor circuit down to the last volt. The full name is Bipolar Junction Transistor, BJT. And the structure is simpler than the name, 3 layers of silicon. Take an N-type layer, then a very thin P-type layer, then another N-type layer, N, P, N. Each layer gets a terminal, and each terminal gets a name. The emitter, which emits the charge carriers, the collector, which collects them, and in the middle, the base, the thin control layer. Keep that word in mind, thin. The base being thin is the entire secret of how a transistor works. Swap the layers, P and P, and you get the second family, the PNP transistor. On the symbol, the arrow always sits on the emitter. For NPN, the arrow points outward. Here is a little memory trick, NPN, not pointing IN. We will work with the NPN, the workhorse of electronics. So how does it actually behave? Picture a thick water pipe with a big flow running through it, and a valve on that pipe. The flow in the pipe is the collector current, the gentle force you apply to turn the valve handle, that is the base current. A tiny twist of the handle and the flow changes enormously. Notice what the valve does not do. It does not create the water pressure. The pump does that, and in our circuits, the supply does that. The transistor does not create power, it controls it. And the leverage of that handle, how much flow you command per unit of effort, that is the famous beta. Let us turn that picture into equations, slowly. Beta is the current gain. The collector current is beta times the base current. I sub C equals beta times I sub B. Typical betas run from 50 up to a few hundred, so the collector current is 50 to a few hundred times larger than the base current. Now, where do these currents go? Into the device flow I sub B and I sub C, and everything that flows in must flow out, through the emitter. So I sub E equals I sub B plus I sub C. That is just Kirchhoff's current law. Substitute I sub C. I sub E equals I sub B plus beta times I sub B, which is beta plus 1 times I sub B. Let us feel these with numbers. Say beta is 200 and the base current is 60 microamps. The collector current, 200 times 60 is 12,000. 12,000 microamps. Slide the decimal 3 places, 12 milliamps. The emitter current, 201 times 60 is 12,060 microamps, which is 12.06 milliamps. Now compare them, 12 and 12.06, almost identical. And that gives us a rule we will use constantly. I sub C is approximately equal to I sub E. The base current is so tiny that it barely shows up in the sum. Before we touch a real circuit, I want to hand you the 2 golden facts that unlock every DC analysis. Fact 1. Look closely at the base-to-emitter junction. P-type material against N-type material. That is a PN junction. That is literally a diode, the very first component of this series. And when it is forward biased, you already know what it drops, 0.7 volts. So V sub BE equals 0.7 volts, always our entry key. Fact 2, you have already met. I sub C equals beta times I sub B. One small notation note. Capital letters like I sub B and V sub CE mean DC values. Lowercase letters mean AC signals. Today is pure DC, so capitals everywhere. Let us gather what we have. The bipolar junction transistor. 3 layers of silicon. Emitter, thin base, collector. In 2 families, NPN and PNP. It behaves like a valve. A tiny base current commands a collector current beta times larger. The bookkeeping is Kirchhoff. I sub E equals I sub B plus I sub C, and because the base share is so tiny, I sub C is approximately I sub E. And carry the 2 golden facts with you everywhere. V sub BE is 0.7 volts, and I sub C is beta times I sub B. Next time, we put the transistor into its first real circuit, the fixed bias circuit, and we solve it completely. Every current, every voltage, down to the last volt. See you there.